So hello, my name is Philip Walton. I'm an engineer on the Chrome and web platform team at Google. And I'm really excited to talk to you all today about this because container queries is actually one of my favorite topics, and it's a feature I've been waiting for a long, long time. And so I have a lot to say about it, so let's dive right in. So container queries are kind of actually a contentious topic. And to fully understand why, you have to know their history. Like many things in this area, their history starts with responsive design. So in 2010, Ethan Marcotte published Responsive Web Design on a list apart, and it changed the way we think about web design forever. Web developers could now build sites with one set of styles and confidently serve those styles to any device. But over the next year or so, you started to see the same questions popping up over and over again. As the web matured and its modular, component-based architecture started to gain popularity, a lot of people were noticing the limitations of using media queries to build responsive designs. In 2013, prominent voices in the community, like Nicholas Gallagher, were starting to suggest that responsive designs should really be component-based rather than viewport-based. And folks like Jonathan Neal even started proposing actual new syntax that could support element-based media queries in CSS. But probably the most influential thing came in April of 2013, a post by Ian Storm Taylor, which was on the front page of Hacker News for a while. And he called media queries a hack. He said they're anti-modular because they couple component definitions to the design and layout of a particular site. He said that what we really need are element queries. And this article is largely responsible for popularizing that term. So a few days after that, after getting slammed with requests for this feature, my colleague and CSS working group member, Tab Atkins, wrote a reply that summarizes the problems with element queries, and it's kind of become the de facto response from the CSS working group whenever developers ask for this feature. So I'll explain Tab's argument in a second, but for now, the main thing I want you to understand is that despite the many valid points that Tab brought up, developers, myself included, still wanted element queries to be a thing. Blog posts continue to be written outlining exactly why element queries are needed. For example, this one from the Filament Group includes a great example that I think perfectly illustrates the problem. So with media queries, you can build a calendar widget like this one, and it works great on both desktop and mobile. But it only works if the calendar widget is rendered in the content area that's the same width as the screen. As you can see here, if you try to put the calendar in a sidebar, it will break because the media queries still report a wide viewport. So what we need is the ability for the calendar to detect that it's in a narrow context and render itself accordingly. And to prove that this isn't just a contrived example, here's a view of Google's newly redesigned calendar.google.com page on desktop. And here's the same calendar rendered in Gmail in the sidebar. Note that this is not only is this calendar being reused in a different view, it's being reused in an entirely different web application, two separate code bases using the same component. So this is a real-world example of how responsive design is clearly about more than just page layouts. It's definitely about component layouts. But since browsers weren't implementing element queries natively, developers started to build polyfills. And since there was no official syntax, each polyfill kind of made up its own syntax, unofficial syntax. And the problem with inventing your own syntax is it creates a potential future compatibility risk, something we see a lot in the JavaScript community. Recent examples like Smushgate come to mind. In 2014, the responsive images community group started a standardization effort for element queries. And after their heroic work getting the picture element standardized in browsers, developers had high hopes. Unfortunately, though, the work was met with a lot of resistance from browser vendors, as well as from the CSS working group. In 2015, Matt Marquis wrote an article in a list apart about the challenges they were facing, and he explained that element queries, at least in their current form, were essentially dead. Given the resistance and challenges related to element queries, the group pivoted to something they thought might be a little bit easier to get through the standard bodies. And so they called it container queries, and thus this new term was born. So instead of having CSS conditionally target an element itself, it targets the element's immediate parent. Unfortunately, while it's true that container queries is less problematic than element queries, they're still problematic, and there was strong resistance from browsers to implement them. But once again, despite no implementation in browsers, developers kept on asking. Chris Coyier hypothesized on Twitter that if element queries were real, they'd be used more often than media queries. And Scott Gell took one step further, and he said that he would almost never use media queries if element queries existed. So the question is, if container queries are useful in design, and if developers clearly want them, why don't they exist? It almost feels like there's this epic battle between web developers and browser makers where neither side fully understands the other. Jeremy Keith describes the sentiment quite well in a post he published about a year ago in his blog. According to him, browser makers always claim they want real-world feedback from actual developers. But when developers tell them that they want container queries, browser makers kind of don't know what to say. And to be honest, in my experience, this is mostly true. So you have browser makers. So I mean, it begs the question: have browser makers just put on their evil goatees? Are we stuck in some weird dystopian timeline where developers don't get any say in the future of the web? So before we get too cynical, let's look back at why browser makers are concerned about container queries. Due to the way CSS works in browsers today, container queries present two primary problems. The first, and I think the one a lot of people are familiar with, is the kind of infinite loop recursion problem. And the second, much less familiar one, is that they actually break the cascade. So consider these two CSS rules. The first one defines an element that defaults to 500 pixels wide. The second conditionally overrides the first rule to say, if the element ever gets larger than 500 pixels wide, make it 499 pixels instead. However, if we make it 499 pixels, then the selector will no longer match. But this means we're back to just the first selector matching. And remember, the first selector tells the browser to make the element 500 pixels wide. And that means the second selector now matches again. And you can see we have a problem. We're in an infinite loop, and there's not an obvious way to resolve this. And note that this problem doesn't just apply to element queries. It also applies to container queries. Oftentimes in CSS, an element's size is determined by the size of its children. This is known as shrink to fit, and it can happen with things like inline block and floats, like in this example. So here we have a container that is floated left and a child element with a declared width of 500 pixels. And since the container is floated, it'll be the same width as its child, so it's also 500 pixels wide. But the next rule says, in the event that the container's width is 500 pixels or greater, the child's width should be set to 499 pixels. However, since the container is floated, changing the child's width to 499 pixels will also change the container's width to 499 pixels. And now you can see that we have the same problem we did before. So that's how container queries can lead to infinite loops. But let's look at how they break fundamental assumptions all browsers currently make about the cascade. In order to understand why this is the case, you have to first have a basic understanding of how browsers take HTML and CSS and render content to the screen. So all browsers currently process HTML and CSS in at least 3 distinct phases: style, layout, and paint. You might have heard of these before. And before I explain them, I want to make sure one thing is clear. These phases are distinct and they're sequential, meaning that each one must completely finish before the next one starts. And that's very important. So to understand why this has to be the case, let's take a look at the style phase. And this part of the talk is going to get a little bit technical, so feel free to zone out if you want to. So in the style phase, the browser goes through every single element in the DOM. It matches it with selectors in the CSS, and then it determines what value should apply to every single CSS property the browser supports. And this is known as the cascade. Note that most browsers support hundreds of CSS properties, and most websites have hundreds, if not thousands, of style rules and DOM elements. So it's critically important that this process can run as efficiently and quickly as possible. So I think most people in this room probably understand how things like specificity and source order work, so I'll go through this quickly. When doing style calculations, you always have to start with the root element in the tree and traverse down. Most of the time, the root element is your HTML, but in this kind of trivial example, the root element is a section. So the reason you have to start at the root element is because some CSS properties are inherited, which means that you have to compute the full set of properties for the parent before you can move on to the child. In this case, only one rule matches the section element, the universal selector, and so those are the only values we apply in the cascade for this element. And actually, that's not quite true. Technically, you also need to list the default values for every CSS property that's not mentioned by any specific rule. And so that looks like this, which is just a little bit verbose. So for the purposes of these examples, I'm going to kind of imply this, and I'm not going to list every single property that the browser supports in every single case. Also, technically, you don't use the kind of shorthand. You use the longhand for all of these properties. But again, this is getting into the details. It's easier just to show the individual properties that match to the rules defined in the CSS. So next we come to the UL, and we'll do the same for it. As you can see, there's 4 properties and 2 rules, and the parent element doesn't have any non-default inheritable properties, so those don't apply. So this is kind of the full set of properties. And it gets more interesting, though, when we get to the LI. As you can see, 2 rules match, but due to source order, the second padding declaration overrides the first one. And so this is the computed set of properties. But we're not quite done yet, because the LI is a child of the UL, and that has a color defined, and color is inheritable. So you have to add that to the list. Anyway, sorry if this is getting too into the weeds, but it's actually really easy to see how this works when you look in your browser's developer tools. All you have to do is select any DOM element, and then you can look at the style pane and see all the properties that are calculated. And I'm going to explain why this is really important. So with regard to this pipeline, now that we're done with style, only now can we start layout. So once again, we begin from the root element, and we do what's called kind of, at least in Chrome, we call this calculating the box tree. But you have to you have to take the full set of cascaded properties for an element, and then you calculate all the kind of rectangular coordinates of everything in the DOM. So in this case, we know that this element is the root element, so it starts out in the top left at 0, 0. And since the default width of a block element is auto, we know that it's going to fill up all the entire space. And in this case, let's just imagine it's 600 pixels wide. We don't yet know the height because we have to go through all of the tree, but we'll get to that next. The UL is very similar. It kind of takes up the same space as the section. But when you get to the LI, now we can actually start kind of developing this box tree. But the important thing to remember here, and none of these details are important. They're all kind of, I'm just kind of faking this example. But the critically important thing to remember is that we can't do layout unless we know what all of the styles are. So we have to do all the styles first, and then we have to do layout. We can't do them at the same time. OK. So the mostly boring part is over. But the main point to understand from all of that, and you'll see why it's important in a second, is you have to do style before layout. So imagine now that we tried to implement container queries. Imagine you're a browser and you're going to implement container queries in your browser rendering engine. So look at this HTML and CSS again. Now let's add another rule that has a container query. So as you can see, this rule conditionally targets LI elements if the parent UL is wide enough. So now let's try to compute what the cascaded property values would be for the LI. If you look closely, you'll notice that there are 2 different values for the flex property. So the question is, which one should be applied? Well, the only way to answer this question is to know how wide the UL is. Is it wider than 500 pixels, or is it not wider than 500 pixels? But since we haven't done layout yet, we don't have that information. If you allow selectors to query based on layout information, then you suddenly go from a sequential rendering pipeline to something like this. In this model, we do style again after layout. But since doing style again might completely change the result of the cascade, you also have to do layout again. But doing layout again may completely change what selectors match, which means you have to do style again. And you have to repeat this process over and over again until everything kind of settles and there are no more changes, and only then can you move on. So this is much, 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 much slower than what we have currently today. And given what I just showed you, I actually think it's a good thing that browsers pushed back and didn't implement container queries when developers asked. If they had, and they had done it exactly how developers wanted, the web would be significantly slower today, and nobody wants that. But there is good news. The reason I said this isn't the darkest timeline is because there are a few events in the history of container queries that I actually skipped over and didn't mention. The truth is, browser makers have actually been working hard to come up with performance solutions to this problem. For example, in 2015, Chrome started implementing a feature called CSS containment. This gives developers a way to tell the browser what parts of their page layout are independent of other parts. And browsers can make lots of rendering optimizations based on this. It also paves the way for potentially avoiding the circularity issue I brought up before. For example, with CSS containment, you can specify that an element's size cannot be affected by any of its descendants, no matter how big or small they might be. And despite the appearance and belief by some that browser makers and web developers are at war, this is definitely not the case. There are actually many examples of browser engineers reaching out to developers and engaging with them to see if the features that they're specifying will actually end up helping solve real problems that the developers are facing. In fact, I know there are plenty of browser engineers here today who would love to talk to all of you, myself included. So continuing on, in 2016, Chrome started working on a feature called Resize Observer, which is one of my absolute favorite new web APIs. Resize Observer lets web developers performantly monitor size changes to any element on the page with a simple callback function. Previously, you could only observe changes to the entire window, but obviously we know that it's possible for elements to change their size even if the window doesn't change. And then, finally, in January of this year, Chrome shipped Resize Observer, which means the feature is now available to over 2 billion users worldwide. So where does that leave us today? While some of these new features may seem cool, we still don't have container queries, right? Well, if you squint your eyes hard enough and you're willing to take the definition of container queries very, very annoyingly literally, then we actually have had container queries since the beginning of CSS. For example, here we define some initial styles for an input and header element. Then we conditionally override these styles based on the state classes that can be applied to these elements' containers. I mean, a selector is essentially a query, right? So these are kind of like container queries. And we can actually use the same concept to build something today that I think is as good, if not even better, than the container queries that developers have been asking for. And I call this responsive components. So let me show you what I mean. Here's the CSS for a component, which uses a hypothetical container query syntax. You start by applying base styles to an element, and these styles apply, they're defined just on the element, so they apply in all situations. Then you add additional styles for when the container is 36 ems or wider, and you add even more styles for when the container is 48 ems or wider. This is really similar to how we do mobile-first design today. Now imagine you replace those hypothetical pseudo-class functions with actual classes. So of course, this isn't magic. It only works if those classes are in the DOM. That's the only way they'll apply. And then they have to be automatically added and removed if the container changes size. It would have to work a little bit like this. In this example, notice how the classes are added and removed from the container as the box gets bigger and then smaller. So the question is, can we make this work? And if so, how? So this is exactly where Resize Observer comes into play and why it's so great. So here's some code that uses Resize Observer that implements the exact logic that I showed you in the previous slide. And it's actually not that much code. So let's step through it. So the first thing you do is create a Resize Observer instance. And then you pass it a callback function. Now this callback function is invoked anytime the elements that you're observing change their size. You get passed a list of elements because sometimes more than one element can change at the same time. And then you're given kind of more details in those. So in the next function, we define a set of breakpoint names and their respective minimum widths. This is just kind of our mapping between the breakpoint names we're going to use and the width that we decide. Then we loop through our list of breakpoints for each changed element. And then if the element's width is larger than the minimum width for that breakpoint, we add the breakpoint class to the element. And if it's smaller than that width, we remove the class. Next, we set a data attribute on the element indicating that the Resize Observer is now active. It's now monitoring this element. Now, this step is technically optional, but it's actually really useful for styling the element in CSS if you want to, because it's often the case that you don't want to show an element until its initial breakpoint is set. Finally, we query for all container elements in the DOM, and we start observing them. So I should point out that the callback only gets invoked for changes to observed elements, so you have to explicitly observe them. It doesn't just, by default, observe all elements. That would be too inefficient. So some of you might share the opinion expressed in this tweet by Zach Leatherman. And while I understand the sentiment, and I do think a pure CSS solution would ultimately be best, I want to point out that even though this technique uses JavaScript, it doesn't depend on it. It doesn't break without it, or if there's any errors with the JavaScript. So if you look at the CSS again, you'll notice that I defined an initial set of base styles that don't have any breakpoint classes attached. So if the user has JavaScript disabled, or if for whatever reason there's an error when trying to run it, these base styles will still apply. It's just like if you load a mobile website on your desktop browser. It might look a little bit weird, but it's still completely usable. So this is actually a textbook example of progressive enhancement. So I don't see any issues with the fact that this strategy uses JavaScript. And even in cases where JavaScript is disabled, or if there's an error running it, we can use CSS to guarantee that our components will always be displayed. Because errors in JavaScript are not going to affect the CSS. This is actually a great kind of use case for CSS. So we define an animation with a 2-second initial delay that fades in for each container element. And then if the JavaScript fails for some reason, the container element will still become visible at most 2 seconds after the CSS is loaded. And when our resize observer code runs, and usually it will run sooner than that, we just remove the animation, and so everything works as normal. Lastly, we add a no-script tag, so if JavaScript is turned off entirely, we show the element no matter what. We don't have that delay. So if you're building a complex web application that requires container queries, there's a good chance your application is already using a component architecture. Whether that's something like React or native web components, you can easily handle dynamic DOM by hooking into your component's lifecycle methods. For example, with custom elements, you can hook into the connected callback, which gets invoked when the element is added to the DOM, and then you can automatically observe new container elements as they're created. As a point, you don't have to worry about unobserving removed elements, because that automatically gets handled by garbage collection. The other really nice thing about using custom elements is then you can give them more meaningful names, like this. You can also really easily define a base container class that all other responsive components can extend, or behaviors that they can mix in. So I know it's not cool to show a slide with minified code at a conference, but the point that I'm hoping to make here is that even though this is a JavaScript-based solution, it's not like you're downloading all of NPM to make it work. 100% of the code to make this work, both the CSS and the JavaScript, is on this slide right here. And this is actually hand transpiled to ES5, so it will work in IE11 as well. And also note, this assumes that the browser supports resize observer. So if you want to use this code on a browser that doesn't support resize observer, you can load a polyfill. But remember, you don't actually have to load the polyfill, because if the browser doesn't support resize observer, or if there's an error, you just get the base styles. So to prove that this technique works, I built a demo site a few months ago that showcases tons of responsive components, and you can resize them in a variety of different ways. And the UI is supposed to kind of mimic common patterns that I see in the wild. So in this case, the sidebars are expandable and collapsible, and this pane is resizable by the user. And so there's no way to handle situations like this with media queries, because you have no idea what the user's preference will be and what size they'll make these content areas. So the demo is built with regular DOM as well as custom elements, so you can see examples of both. And all the source code is clearly linked from the site, so you can dive in and see how it's implemented. And lastly, I want to emphasize that the site works cross-browser. It's not like a Chrome-only thing. It even works in IE, and it even works when JavaScript is turned off. So even though resize observer is Chrome-only, this demo shows that that is not a good enough reason not to use the technique. It can definitely work everywhere. It's progressive enhancement, like I said before. So to summarize the current state of affairs, while CSS container queries don't exist in the form developers have been asking for, there's lots of ways to mimic this behavior with current web technologies. The strategy I've outlined here is what I consider to be the best way to build responsive components today. It's performant, it's easy to implement, it doesn't require any specific JavaScript framework or build tool, and it even works without JavaScript entirely. So now that we've discussed the past and the present, let's take a quick look at the future to see what that might bring. So the good news is that the W3C, through the Web Incubator Community Group, has actually restarted the container query efforts. And this is being led by Tontek from Mozilla, and the new spec is being edited by Tommy Hodgins, who's the creator of the EQCSS polyfill. So while it's impossible to say for sure what the future will bring, let me leave you with a couple of my predictions. First, browsers are definitely not going to be making the web slower. This means that any future container query solution will likely be built on top of existing optimizations like CSS containment and resize observer. Second, I think web components and things like layered APIs will be a big part of this future. I can imagine we ship something like a declarative resize observer element or component that requires strict CSS containment. That way browsers can really easily optimize for it. As a side note, if you're not familiar with layered web APIs, talk to me about this afterwards. It's a really exciting new idea. Finally, I think that some of the experimentation browsers are doing currently with parallel rendering and async layout might lead to breakthroughs in the efficiency we can do layout. But even if that happens, I still don't think container queries will be implemented if they require a multipass rendering. I mean, you can imagine if layout suddenly becomes 10 times faster in some browser, I don't think that browser is then going to lose that entire speed gain to implement a slow feature. Most likely, they would be just shouting from the rooftops about how much faster their browser is than the competition. So for some final thoughts. First of all, Resize Observer finally gives us the ability to build ultra-performant, truly responsive components. So please try out the API, and if you build anything cool, definitely share it. Second, CSS containment is an amazing advancement in layout performance, and it will likely shape the future of container queries. If you haven't used it, you should try that out as well. It can make your site feel much, much faster. Third, browser makers and web developers definitely shouldn't feel like they're at war with each other. They should be working together. But don't forget that while browser makers want to please web developers, their ultimate responsibility is to their users. And that's who we as web developers should care most about as well. So let's make the web faster for everybody. Thank you.